In this video, I am going to show you the complete design and detailing of reinforced concrete flat plate slab using ETABS. And in the video, we will also use Excel for shear check of the slab. The given parameters are shown: FC prime 5 KSI, FI 60, floor height is 10 feet, and we have to design the first floor slab in the 3-story building. Columns are 12 by 36, center to center span is 12 feet. The occupancy of the building is residential. SDL load is 36 PSF, plain beam is 12 by 24. We have to use UPC 97 and ACI code. First, open the ETABS and go to new model. Defining the grids in X and Y direction. Number of stories is 3 and the story height is 10 feet. Defining material properties of concrete as 5 KSI or 5000 PSI. You need to check the material property data. Defining the reinforced bar. 60 KSI. Okay. Let's rename it as G60 deformed so that we can identify our material easily. Now we will need to define the frame sections. First, defining the column section. The column is 12 by 36 as given. Material was 5 KSI. The property modifiers according to ACI code incorporating crack moment of inertia is 0.7 of the gross moment of inertia. So we incorporate that using property modifiers. Modify show rebar, in which we will select our rebar material. Click on OK. You may delete multiple properties which will not be useful to you. For now I am leaving them. Now naming the slab. In order to find the slab thickness, we will use ACI table. The slab is without drop panels and the slab consists of exterior and interior panels, but conservatively we will use exterior panels so that our slab has a uniform thickness. An exterior panel will give a higher value of thickness, and it is without edge beams and the steel is 60 KSI. So we have to divide the clear span divided by 30 in order to get our thickness or initial iteration of thickness. You may revise the cross section if the slab fails in deflection, flexure or punching shear, which I will check in the video when I have designed the slab. For now I am defining the slab as 5 inches, which we calculated. Property modifiers. In order to understand the difference between shell thin and membrane, you have to go to the previous videos for the ETABS tutorial, whose link is given in the description of the video. For time being, I am assuming we have gone through the previous videos. So now we will incorporate the crack moment of inertia for the slab using ACI code, which is 0.25. Click OK. You may delete the other properties which are not useful to you, so that there are less chances of mistake. Now start modeling the structure. Since the grid lines lie at the centroid of the column, so you can always draw the columns like that, the way I drew. Now you see we have to select the slab which we defined. Now for the cantilever part of the slab, which is 6 feet given in the question, we will draw a dummy beam with 0 stiffness, which is just for drawing the slab boundaries. 6 feet multiplied by 12 gives you 72 inches. So give the offset dimension of the dummy line. Similarly for the other side. Now we will draw the slab using the line. Now you may delete the reference lines which you marked. Now for slab meshing, in order to know how the slab is meshed, you need to go to previous videos. For time being, I am assuming you have gone through them. So now, according to the slab meshing rules, the slab shall be meshed in maximum 3 feet by 3 feet area. Since the slab panel is 12 feet by 12 feet, so dividing it by 3 feet gives you 4 by 4 areas in x and y direction. Since the slab meshing lines shall be continuous, so you need to select the joints, and for the cantilever part, mesh it by extending the lines from the joint. So the cantilever part is meshed in y direction. For the x direction, it is of 6 feet. So at least 2 areas are required of 3 feet by 3 feet areas. No meshing required in y direction since it was already meshed. So now we have done the meshing of the slab manually. For auto meshing options, you may click on the video whose link is given in the description. Now defining the load patterns. The load patterns for the finishes, which is a super dead load, now we need to assign the loads on the slabs. First of all, select all the slab panels by using the selection option. Go to shell loads and click on live. Now going to UBC 97, which we were advised to use, the live load for residential structure which we were given is 40 PSF. You may click on replace existing loads, so any existing loads will be deleted. Now click on previous selection and assign the 36 PSF finishes load. So now we are done with assigning the loads to the panels. You have to verify the loads by clicking on a panel and right click. Since the loads are now assigned to all of the panels, we may proceed to the next step. We have to assign diaphragm to the slab. The diaphragm is usually assigned in a non-prismatic or irregular structure, but our structure was regular, so it was not necessary to assign the diaphragm. Make sure that for concrete structures the diaphragm selected has a rigid property. Now selecting the design code for the slab so that our combinations will be according to ACI 31808. Now add default design combinations. Click on concrete slab. Since we are designing the slab, check the combinations according to ACI code. You have to add a long-term deflection combination so that we may check that the slab is not failing in deflection. Now the multiplier for the sustained loads is 3 and for live loads is 1.5. Now we have to draw the slab strips for column and middle strip. The width of the column strip is quarter of shorter span in both directions, but since our both directions are of 12 feet, so the column strip width is 25% of the 12 feet. That means 36 inches on each span, while the middle strip will be the remainder or area in the slab span. Now in order to see the strip width, you may turn on the show width option. Click on apply and OK. Now draw the middle strip. Now for the remaining middle strip, the total cantilever span is 6 feet and the column strip is occupying 3 feet from those 6 feet. So the remaining middle strip will be of 36 inches. That makes it 3 feet. Since it's on one side only, so you may neglect the left strip width. Now for the left side, you may neglect the right strip width. Now turn off the strips and we have to draw the strips in the other direction for the reinforcement to be designed in other direction as well. Note that the strip width of the column strip remains same in both the directions, since we are considering the 25% of the column strip width of the lesser span in both directions. Now drawing the middle strip. Now turn off the slab, column and beams so that strips can be selected easily. Now you need to select the column strip in layer A first, then go to design Concrete slab overrides and strip base and assign the material for the rebar. Click on OK. Now select the middle strip in the layer A. Go to design, concrete slab design and strip based. Now select the material. Same procedure shall be repeated for the strip layer B. Select the middle strip or the column strip first. It's your choice. Since our ultimate goal is to assign the material for the rebar in the strip. Now going for the middle strip. So now we are done with drawing the strips and assigning the strips the proper material for the rebar selection. So that area of steel will be calculated according to the strength or Fy of the steel assigned. Now show the width of design layer A and B. Now select the slab and replicate it to the third story. Since we were drawing in third story, so we replicated into second story. Now for the lowermost story there is slab on grade, so we need to replicate the frame only and draw plain beam over there. Since the slab will not be a reinforced one, it will be a slab on grade, so we replicate the frame only, and now we will have to draw the plain beams. You may check the alignment of the columns in 3D that the columns are continuous and joints are properly formed. Now adding the property of the plinth beam. The property modifiers according to ACI code, incorporating the cracked moment of inertia. We take the torsional constant as 0.001 so that no torsion is incorporated in the beam. Select beam for reinforcement, click on OK. Since our beams lie on the grid, so I may use a quick modeling technique here. Take the beam and hover over all the grids so that the beam is drawn over the grids. Now turn on all the visibility options. So the structure is now modeled. Now you may edit the story names for your easiness to understand. Let's name the story 1 as ground, the first floor, and then the second floor. Our scope is to design the first floor only. Click on OK. Now run the analysis and then save the structure. Since it's example 2, for example 1, you may click on the video in description. The deflection according to ACI code is L by 240. or the cantilever part deflection is slightly higher, but conservatively you may take the limit for the rest of the slab and revise thickness if it is required. Check the deflection at long term. On the bottom left of the screen, you may note the maximum values. However, our concern is only the absolute value, so the deflection is greater than our limit of 0.6. So now we have many options. Either we revise the strength of the concrete, increase the strength of the steel, or simply increase the slab thickness. You may increase the slab thickness stepwise, like you may have to increase in iterations. First you may increase it to 5.5 inch, then 6 inch, then 7 inch, but just for demonstration purposes I am directly increasing it to 8 inches. Now run the analysis and do the checks again, that whether the slab pass or not. Long term deflection, click on apply. Okay, now the deflection maximum coming out is minus 0.56, that is in the cantilever part. The coordinates are given in bracket. Which is under control and within the limits. Now in the next, since the slab has passed the deflection check, so we may check the punching shear, whether the columns are not punching in the slab. For that you need to design the slab first. So now the slab is designed. Display the punching shear check. The punching shear check, the numbers displayed shall be less than 1, which is the ratio of your capacity of the slab to the design load, which shall be less than 1. Now you may use the Excel sheet for the cross check. Since the Excel sheet I am providing in the description is in MKS system, so you may change the ETABS units into MKS system or SI system. Click on the most critical column. You may need to zoom for that. Right click and you may get the parameters we have to input in the sheet, which will be a cross check, or you can say a manual check for the punching shear. The thickness of the slab and the effective depth. Cx and Cy are the column dimensions in X and Y. It is important that you input the correct dimension in the correct axis, so that the moment will be input according to that. Fy is 420 megapascal and Fc prime is 28. It's 35 megapascals for 5 ksi. So now the shear force is to be put in Pu and the moments in y and x direction according to ETABS. You may have to carefully input the directions, whether it is mu2 or mu3. For Cx direction the moment is mux, and for Cy direction the moment is muy. You can also view the stripped moment diagram for that case if you don't understand for which direction which moment shall be assigned. Usually for the wider columns side the moment is higher. Now we are done with giving the parameters to the sheet. So the sheet gives you various parameters. Punching shear reinforcement is not required. If the slab was not adequate in punching shear, you may use iterations here, whether how to provide the reinforcement for the punching, which I will explain in the next video for the design of drop panel and the slabs. For time being, we are okay with the punching shear check, so no punching reinforcement is required. As the slab's concrete own strength is greater than, you may cross check the ratio of 501 divided by 0.75 gives you the concrete strength 5 EC divided by the load, which is 15.6, 159 point something. 1 divided by the answer, since I had to take the inverse of that thing. The answer would approximately be equal to the one given by the ETABS, which was something like 0.3. You can see other things in this sheet as well. So now we are done with punching shear, so that was not necessary to calculate the ratio. Now you need to display the flexure design. It is important to click on impose minimum reinforcements so that ETABS give minimum reinforcement where no reinforcement was required. Now select a top bottom mesh for the slab. Use the units as FPS system. Since there is a bug in this ETABS, so you need to click on none and then again click on typical uniform reinforcement so that the option unfreezes for the spacing input. So now no extra reinforcement is required. That means we have over designed the slab. So the increase the thickness, increase the spacing of the bars. Still no extra reinforcement required. That means we have over designed the slab. We need to reduce the steel in the slab. Let's make it number 3 bar at 12 inches. So now we are getting a lot of extra reinforcement. Let's make the extra reinforcement as well as for number 3. So now the extra reinforcement is further more increased. That means the slab is complicated and it is difficult to construct it on site. So we have to slightly increase the mesh area of steel density so that the extra reinforcement is not that much high. You may reduce the scale factor of the diagram for easier visibility. Hide the bottom rebar for time being. So the top reinforcement is almost required everywhere where there is negative moment. You may increase the graphic font size for clear visibility. Now you can see the numbers on the screen without zooming or zooming slightly. Again display the flexure diagram. You may turn off the fill diagram and only see the values. The blue color shows that it is the reinforcing bar. Show bottom bar of layer A and B. a lot of extra reinforcement is coming. So now we need to revise the mesh. Let's just increase the mesh and decrease the spacing to 8 inches. Still a lot of extra reinforcement is coming, so decrease the spacing. Since designing is an iterative process, you have to repeat the procedures again and again. Let's make the spacing to 6 inches. Very less extra reinforcement is coming, so we need to increase the spacing a bit. You can make it 7.5 inches if you want to, but it would be difficult on site to execute. Let's keep it 8 and 7 inch in other different directions. But again, the mesh is difficult to execute on site, so you may keep the mesh same if you want to. Now for detailing purposes, the top negative reinforcing bar shall be extended from the face of the column to at least 1/3 of the span in longer direction. Let's consider two span. If the span A is longer, then in span B, the bar shall be extended 1/3 of the span A. In other words, in both the spans, the bar shall be extended 1/3 of the longer span. The blue color shown here is the reinforcing bar, and when you hover mouse over it, then the black line shows the extent of the bar, that the bar will be distributed in that direction. It is easier in the latest version of ETABS to understand the distribution of the bar. This option is also incorporated in SAFE, whose tutorials will be uploaded to the channel soon. So now we will proceed with the detailing. Now you can see the distribution of the bar is 1/3 of the span in both the direction of the column, and the length of the bar is also 1/3 of the span in both the directions. Now we will start detailing the slab. Since the reinforcing is for layer A and B, which the draftsman will later combine as a single floor framing plan, for now simplicity and demonstration purposes, I have developed two different plans, one for reinforcement layer A and the other one for reinforcement layer B. Now this is the mesh of your slab, that is dia 3 or number 3 bar at 7 in center to center in both the direction. That is a top bottom mesh and is usually provided in the slabs thicker than 5 or 6 inches, and the extra reinforcement will be imposed on that. So now we have provided the mesh. We need to provide or label the extra bars. Turn off the layer B. Nothing in layer A is left. So you may delete the bars which are drawn here, as ETABS is giving nothing or no extra reinforcement. In other words, the mesh provided is enough for reinforcement in layer A. The extra reinforcement is coming out in layer B, as the mesh will not be sufficient for layer B, so we may provide the extra reinforcement there. You have seen in the video that I have done a lot of iterations so that the extra reinforcement does not come too much or does not come nothing at all. There shall be a balance in the things always. The extra bars shall not be too high or shall not be too less. The elevation of the slab is 10 feet from the ground. Since I continue to delete the extra reinforcement bars since nothing is required in layer A, which was already drawn by my draftsman. So I am nearly done with deleting the bars, extra reinforcement bars, which were not required in layer A. The tag is 8 inches thick. Now we proceed to detailing of the reinforcement layer B, where we are sure that we are getting the extra bars. Show top bottom both. Since we are getting no bottom rebar, so the extra bars are only the top. 2, 4, 3 and bars are similar since the slab is symmetric. So we proceed to detailing. To number 3, extra top. 4 number 3, 3 number 3. You may specify the spacing of the bars, but since the bars are too less in number and the span is larger, the spacing will be slightly higher of the extra bars. So it's no need to mention the spacing. You may also mention the number of the bars. It's all depending on you. While for the main mesh, the spacing must not be greater than 18 inches according to ACI code. Since these are only extra bars, so the spacing can be greater than 18 inches, or just in terms of number of bars, whether how many bars are required, whether it be 8, 10 or 3 or 2 bars. Sometimes designers neglect the 3 or 2 bars, but it's always okay to provide those bars so that the vetting engineer may not get the chance to question whether the reinforcement is provided lesser than the required. So it's always safe side that you provide what is required. 3 number 3, actually it was number 3, and 4 number 3. To number 3. So now we are done with placing the extra bars in the detailing sheet. No bottom reinforcement bar was found in the design. Now you may delete the extra bars later on. The detailing sheet was already drawn by me. If you want to learn how to use AutoCAD in detail, you have to subscribe to the channel since I will be uploading AutoCAD tutorials and other software tutorials such as Revit soon on the channel. Now before printing the sheet, go to layout, press Ctrl P. You will get a layout. Click on preview if you want to preview it. Click on landscape if you want it in landscape. Diagrams are usually in landscape since a lot of extra space is being wasted as margins. So double click on the paper space and click on extends and then click cancel. Click on zoom command and press W so that it would be zoomed to window. Whatever you draw, adjust and then click on preview. So the sheet is okay. Now you may convert it into a PDF or simply print it using a printer. For now I am converting it into PDF. So now we are done with printing or converting into PDF. Subscribe to the channel for much more tutorials and engineering related content to come soon. Thank you for watching.